So steady state error when the input is unit parabolic signal. So here we know the steady state error calculation, like here steady state error can be written as ES is equal to limit S tends to 0 S into R of S divided by 1 plus G of S into H of S, and the input is given as unit parabolic signal. So therefore R of S will be now 1 by S cube. So therefore steady state error can be written as limit S tends to 0 S into 1 by S cube divided by 1 plus G of S into H of S. So here this S and S cube will be cancelled out here 2 times, so square term will be left over in the denominator. So therefore ESS will be now limit S tends to 0 1 by S square plus S square into G of S into H of S. So applying the limit values in the denominator, so that this term will become 0, and directly I am writing here 1 by limit S tends to 0 S square into G of S into H of S. So this can be written as 1 by K A, acceleration error constant, where K is the limit S tends to 0 S square into G of S into H of S. So let us check for type 0 and type 1 systems. So for type 0 system, Ka will be limit S tends to 0 S square into G of S H of S. So therefore limit S tends to 0 S square, and G of S into H of S can be written as K into numerator terms Z1 Z2 Z3 so on divided by denominator terms P1 P2 P3 so on. So when we put limit S tends to 0 here, this entire term will become 0. So therefore ESS will be equal to 1 by Ka, where 1 by Ka is equal to 0, so that will be infinity. So for type 0 systems, for unit parabolic input, the steady state error is infinity. Now for type 1 system, Ka will be here limit S tends to 0 S square of G of S into H of S. So for type 1 system, what we have to take here, the denominator we need to put S term here. So this will be Z1 Z2 Z3 so on divided by S to the power of 1, because it is a type 1 system. So therefore S plus P1 S plus P2 S plus P3 so on. So here this square term and this one will be getting cancelled out, and anyway this will become 0. So therefore steady state error will be 1 by Ka, which is nothing but 1 by 0, which is equal to infinity. So for type 1 system also the steady state error becomes 0. Next, for type 2 system, Ka is equal to limit S tends to 0 S square G of S into H of S. So this can be written as, so for type 2 system we need to put S square term in the denominator. So therefore s plus z3 so on divided by s square into s plus p1 into s plus p2 into s plus p3 so on. So this square term will be getting cancelled out, and now this will become a constant. So therefore steady state error will be now 1 by Ka, which is nothing but a constant term. So there will be steady state error for type 2 system. So for type 2 system, when the input is unit parabolic signal, then there will be a constant steady state error. So we'll see for type 3 system. So limit s tends to 0, this is Ka value I am writing. So s square of g of s into h of s. So here limit s tends to 0, s square into k into s plus z1, s plus z2, s plus z3 so on divided by type 3 system. So I am writing s power of 3 and s plus p1 and s plus p2 and s plus p3 so on. So this square term will cancel with 2 times of s, and here we are having the value of steady state error. So the Ka value will be now infinity, and ESS will be here 1 by Ka, which is nothing but 1 by infinity, which is equal to 0. So for in steady state error with type number 3 and more than 3 and type number 3 and more than 3, then for the unit parabolic signal, for the input is unit parabolic signal, then the value of Ka will be infinity and the steady state error will become zeros. So this is a conclusion from this unit parabolic signal. So the conclusion of all these error constants and as well as steady state error values will be as shown in these tables, and error constants are represented as Kp, Kv and Ka, and type number systems are represented in horizontal manner, type 0, type 1, type 2 and type 3. So for type 0 system, the error constant will be constant here, and for type 1 it is infinity, and type 2 also it is infinity, and type 3 will be infinity. So for type 0 system, the velocity error constant will be 0, and this will be constant here, and above type 2 and above it will be infinity. So here in this case 0, 0, and this is the constant value for type 2 system, and above type 3 this will be infinity. So these are the error constants versus type number of a system, and the steady state error versus input signals will be as shown in this figure, in this diagram table. This will be 1 by 1 plus Kp, which is constant. Kp is a constant, and all the above are zeros. And for unit ramp signal, this will be infinity, and this is 1 by Kv, and all above will be zeros. So here it will be infinity and infinity, and this is 1 by Ka, and this will become 0. So for unit step input for type 0 system having steady state error constant, which is equal to 1 by 1 plus Kp, and above 1 and above, the type number 1 and above, that will be 0. And for unit ramp signal for type 0 system, this steady state error will be infinity, and for type 1 system it is 1 by Kv. For type 2 and above, this will be 0. So similarly for unit parabolic signal, for type 0 and type 1, the error steady state error constant is infinity. For type 2 system it is constant. For type 3 and above, this will be 0. So this is related to the steady state error constants.